So I'm now going to walk through assignment 2B, the skeletons and the unit test. The app itself works just like the previous apps. The beings and the Palantiri will be displayed visually, and they'll blink as they go through the paces of doing the app logic. So that doesn't change. Likewise, the Android test, the one here, works the same. But what I want to focus on first is the unit test, fair semaphore unit test, because that's important to understand if you want to get your specific notification semaphore, fair semaphore, implemented properly. So let's go ahead and run this test. You can see here that this goes ahead and goes through all the various parts of this test. Probably the most important of these unit tests are test fairness with interrupts and test fairness. Those are the things that are actually checking to make sure that the fair semaphore implementation works in a, quote, fair way, which is, of course, what it needs to do. And this is basically just a diagnostic that's printed as it runs, in illustrating how things are being added to the queue and what happens when interrupts occur and so on. So as you can see, everything turned green here, which indicates that the implementation was correct. If there are problems with your implementation, you will get red marks, and hopefully you'll get exceptions that will explain to you why your test is not working properly. So make sure you understand how to run this test. Now that we've walked through the fair semaphore unit test, I'll go ahead and show you the skeletons. The skeletons are largely the same as assignment 2A with one exception, and that's, of course, adding in a fair semaphore in the model layer. Before you address that, though, make sure you go over and copy your solution for the presenter layer files, being async task, and Palantiri presenter. Copy that from the assignment 2A solution that you turned in already, making sure to address my comments, of course, first. Here's the Palantiri manager implementation. It will be largely the same. You'll have to go ahead and copy in what you did before. The only difference is that you'll be using a fair semaphore instead of a simple semaphore. Once again, make sure you address my comments from previous iterations. Let's go take a look at the fair semaphore implementation. This is what you actually have to fill in. The implementation will be using the so-called specific notification pattern. You can get a paper that describes that pattern here at my website. I'll also be putting out a video later in the week that talks in more detail about this pattern. The undergrads need to use built-in monitor objects, and the grad students should use reentrant lock and condition object, which is a bit more complicated, but the logic is more or less the same. Here's the skeleton itself. Come down here, you'll have to add in a count of the number of available permits. Make sure that this works properly in the context of multi-threading. Hopefully you understand what that means by now, because that's very similar to what you did for assignment 1C. The grad students are going to have to use this class called waiter. Undergrads can ignore this class. You'll be using built-in monitor objects instead. But the grad students have to use this waiter class. And as you can see, it defines a lock, which is a reentrant lock, and a condition, which is allocated from the reentrant lock using the new condition factory method. And this will then be used for synchronization inside of a queue, which we call the wait queue. The grad students will also have to define a reentrant lock to protect critical sections in the methods below. The undergrads, of course, can simply synchronize on this in order to do that. You then have to go ahead and define a wait queue that will be used to keep track of the waiters in a FIFO list. I recommend using a linked list to do this, probably the easiest thing to do. Grad students should make this a list of waiter objects, the ones that are defined up here. The undergrads should make this a list of objects, just the good old Java object class. Then go ahead and fill in the constructor to initialize the fields in the class. The grads and the ugrads will have slightly different implementations, of course, but it's along the same lines. You'll have to then implement the acquire uninterruptibly method, which should be done very similar to what you've done in assignment 2A or 1C. Of course, in order for this to work, you have to first implement the acquire method. And so this is very simple once you have acquire working properly. Here's acquire. I've actually implemented the skeleton for you here. So you come in, you check for interrupts. If you've been interrupted, you throw an interrupt. Otherwise, you try to get a permit, which is the fast path we'll talk about in a moment. And if you are successful in getting a permit, you're done. If you're unsuccessful at getting a permit through the fast path, then you'll have to block until a permit is available by calling the wait for permit method. So let's go ahead and talk briefly about these two method. This is where the bulk of the implementation goes, as well as, of course, in release. So try to get permit. This is the fast path where the method doesn't need to block, and it won't need to block if there are no waiters in the queue or if there are permits available. So if there are permits and there are no waiters, then we can go ahead and grab a permit very quickly and we'll be done. So this is something that doesn't require blocking. You just have to synchronize properly and do those checks. You'll return true if you obtained a permit, false otherwise, and that will be used up here in the try to get permit check. Assuming, for sake of argument, that we are unable to get a permit because they're all in use, then we're going to go ahead and wait for a permit. So this is where the more complicated logic goes. This handles the case where we need to block since there's already waiters in the queue or there are no permits available. So you'll have to implement the specific notification pattern here. I'll be talking more about that in a different lesson, but in a nutshell, you'll have to create a wait node or a wait lock, whatever you want to call it, and that will then be put into the wait queue. And you'll have to do this very carefully so you don't end up with self-deadlock. And then the thread that called wait for permit will go ahead and block waiting for that object in the queue to be notified or signaled, depending on whether you're doing the undergrad or the grad version, respectively. So how does it get signaled? Well, of course, some other thread is going to have to call release. Here's the release implementation. Wait for permit is pretty complicated and subtle. Release is subtle, but not too complicated. There's not a whole lot of code going on here. And so what you do in release is you basically check to see if there's anything that's in the queue. If there is something if there's nothing in the queue, then you simply increment the permit count by 1 so that someone else can be released. If there is if there's something in the queue, then you're going to have to go ahead and notify the something in the queue to wake up. And you'll do that by either calling notify on it or you'll do it by calling signal. Depends on which one you want to do, whether you're doing the undergrad or the grad version, respectively. So those are the basic methods in this class. We'll talk more about the pattern in a little bit, another lesson that we'll talk about. But it should be pretty straightforward, and hopefully you won't have any problems making it work. I have to mention, however, that this assignment is a lot more complicated and subtle than the previous ones because the conditions for race conditions and other subtleties are problematic. So make sure that you watch the videos, make sure that you read the file, the one that's called the specific notification paper, and come to office hours and ask lots of questions because it'll be hard. And also make sure that you are thorough and always run the fairness checker in the FAIR semaphore unit test to see whether your implementation is working properly.